Okay, let's continue. Our next speaker is Professor Nai Chung LEUNG from the Chinese University of Hong Kong. The title is SYZ measure symmetry. Let's welcome.
Thank you. First, thank you for giving me this opportunity to present my work on mirror symmetry, more specifically on SYZ mirror symmetry. Okay, so we briefly explain mirror symmetry, which is originated in physics on the study of string theory. There are many people working on this area, including some important figures like Waffa and Witten. And the main object to study are Calabi-Yau geometry, and they are manifold, Kähler manifold with zero Ricci curvature. And by the result theorem of Yau, and you can always solve that equation as long as topology is allowing you to do so. And the so-called mirror symmetry is for Calabi-Yau manifold. The string theory has two different topological sectors called the A model and B model. And the symmetry is the two Calabi-Yau manifolds of the same dimension, and such that these two models switch with each other under the duality. And that they receive a quantum correction on the A side. Mathematically speaking, and this is a duality between the symplectic geometry of one Calabi-Yau manifold Y and the complex geometry of the other Calabi-Yau manifold Y check. And there are also a huge number of great mathematicians working on this area, including Maxime Kontsevich and S.T. Yau and so on, many people. And in this mathematical way of explaining it, so-called the quantum corrections are Gromov-Witten invariants or open Gromov-Witten invariants in the open sector. All right, so in mathematics, the mirror symmetry between symplectic geometry and complex geometry, these predictions has induced a huge amount of new mathematics that are developed in the last 20 years. I include some of the important new mathematics that are here. On the symplectic side, there are this floor theory, so-called the Fukaya category, and there was a lot of people's work to really, nowadays we have a good, even the definition is a very difficult problem to understand, and also we have a lot of good calculation and understand a lot now. And it involved like the introduction and the study of Gromov-Witten invariant, which count the holomorphic curve, and also the open Gromov-Witten invariant, which is a much more complicated subject to handle. On the complex geometry side, the analog, the mirrors statement for the Fukaya category become a very different object. It's called the derived category of a coherent shift on the complex manifold Y check, which was denoted as dy. And there are some geometric objects which has been studied even before this mirror symmetry was introduced. It's called the Hermitian-Yang-Mills equations. And here they involve so-called deformed Hermitian-Yang-Mills equations, and many other subjects that are introduced, and including the topology, physics, quantization, and number theory. Many new mathematics come up. And these are the objects that we'll discuss a lot more in today's talk. And in the middle, I wrote down the SYZ transform, which is you can think about is a geometry way of introducing a transformation like a Fourier transform to interchange this completely different type of physics and geometry. Okay, so we're going to explain this Hermitian-Yang-Mills equation first. In fact, this is a work that I did many years ago. It's called the deformed Hermitian-Yang-Mills equations, denoted as DHYM. The geometry underlying this problem is a holomorphic bundle on a Kähler manifold. So the bundle is called E, the Kähler manifold Y, and the Kähler form comes from an ample line bundle called L. And this is a very classical, famous theorem of Donaldson, Woudenberg, and Yau. They says that you can solve these Hermitian-Yang-Mills equations. This is the equation on the right, that the trace of the curvature is called the F, Trace of the curvature is constant. Constant in terms of constant along the space and constant along the fiber directions. So the trace of the curvature is constant. It's a Yang-Mills equation. And the theorem says that you can always solve it exactly whenever the bundle is called Mumford stable, which is a notion introduced in algebraic geometry by Mumford. So the Mumford stable is a much easier problem to understand. It's just comparing the degree, which is the first Chern class of the bundle, averaged by the rank of the bundle. Compare this first Chern class with subbundles. Okay, and it turned out that this is enough to solve the equations. Okay, now the more natural question is not Mumford stable; it's called the Giesecke stable, and the reason is that Mumford introduced this notion in order to understand the moduli problem, to construct moduli space called the geometric invariant theory. And to do so, you really need to look at not just the first Chern class, you have to look at all the Chern classes together, which is this combination used in the Riemann-Roch formula. You need to use all the Chern classes of E, at least for large K. So the dominating term, the first order term, is the first Chern class, which is a Mumford stable. So in a way, the Mumford stability is really a linearized version of the full stability, which are really used in algebraic geometry called the Giesecke stable. So the natural question is, okay, is that an analog from the more differential geometric perspective? Whether there is an equation which governs this property. Okay, and that is my first work basically. So many years ago, I solved this problem, and it's when the Jordan-Holder filtration of the bundle is smooth. So you under some smoothness assumption to solve the equation. I proved that you can solve that whenever it's a Giesecke stable, you solve exactly these following equations. So this is a fully nonlinear equation with a Monchaux-Bemper type, because the curvature is roughly like dd bar of the log H. So this is determinant of dd bar of the metric. So you want that to be a constant, at least for large enough K. Okay. So two remark here. First of all, this is a fully nonlinear system of PDE, which makes it extremely difficult to solve. But we are only solving it for large enough K. And I'll explain the solution, the idea of proving it in a second. But even though I did it many years ago, but there are lots of some of the very recent development. As I explained that was also now become important in mirror symmetry. There was a study by Collins and Yao in the last 7, 8 years that this is related to a quantum notion about stability. It's called Dirichlet stability, which is a notion introduced first by Michael Douglas by the study of string theory, and then rigorously defined and studied by Dirichlet. And that's an important notion in mirror symmetry. And they are understanding the relation between the deformed Hermitian Yang-Mills equation, which is the one that I wrote down here, and Dirichlet stability notion. Okay. All right, let me say a few words about how to solve the equation. As I explained that this is an equation with the fully nonlinear equations are Monchaux-Bemper type, but this is a system which makes it difficult. That's the reason. And the way to prove it is you try to understand what happened when K really go to infinity, when everything blow up. And then we have to understand what we expect that things to blow up. You have to understand that we are algebraic geometry. That's where the Giesecke stability is used. Okay. So I have to first get a control of what the solution might look like at infinity. And then you have to use some singular perturbation argument to prove that you can do the singular perturbation to solve the equations. And all the obstruction is killed exactly using algebraic geometry by this notion about Giesecke stability. So it's a very tricky singular perturbation argument. And that is how the equation is being solved. Okay. So here's some other work. This is a Yao-Sarsdorf formula. So these are a few words I did earlier related to mirror symmetry, string theory, and we'll explain this formula in a second. Okay, so let me first explain state the theorem. Okay, it's a theorem I work with Jim Bryant. It says that on the K-free surface S, we want to count the number of holomorphic curves. These are usually called Gromov-Witten invariants. Okay, and in fact, for K-free surface, the usual Gromov-Witten invariant is always 0. But it turned out that Yau-Saz have an amazing formula. Let me show you the formula first. The one here. Okay. So the formula says the following: that if you just try to count it, sometimes, most of the time it's 0. But if it's not 0, then it's exactly some particular number. And those numbers will form a modular form. And that's the amazing thing. And this is the first time that we see modular form count for counting enumerative question in dimension higher than 1. Okay? And the formula was discovered by Yau and Sarsdorf by studying string theory on K-free surfaces. This is again a physically motivated argument to really find out this amazing formula. And then we'll prove this even in the high genus case. Okay, so we are under the assumption that the class is not divisible, so it's not multiple of some other integral class. So first, the statement is that if you try to count the number of curves in a fixed class of some particular genus, okay, so the thing is that usually this is 0. Well, if this is not 0, then this number is called NGD. Okay, first of all, you have to explain what that even means. So this is where the first thing we did is to develop this reduced Gromov-Witten invariance, to really say that using twisted geometry and hypercadal geometry to really rigorously define what that means by counting curve, even though most of the time it's 0. Okay? And then the second thing is that this number turned out to be independent of the K-free surface, even also independent of the class. Only depending on the intersection number of the class, the topological number. That's it. And then the more amazing thing is this: if you form the generating function for each genus, and that is a module form. It's called quasi-module form. This is the module form notation. Explicitly, this is this notation. Okay? So it's a very explicit thing, and it's modularity. Okay? So the first thing to prove is you have to understand that what does even mean using hypercadal geometry to define this reduced invariance. And then the thing is that then how to compute it, how to get all this module form, this surprising formula. And the first is, well, we have to use the fact that this is independent of the particular surface. So we have to use various arguments to show that now we only need to look at a very specific K-free surface. Well, even that is difficult. We have to break the K-free surface into 2 rational elliptic surfaces. Okay, that becomes an easier question because now that surface becomes birational to CP2. And birational transformation between CP2 are given by chromolar transformation. And then you have to use a lot of chromolar transformation techniques to really, that involve a huge amount of tricky transformation to reduce to finally a very trivial statement that on the plane, there's only one line passing through 2 points. Okay? So we are basically looking at this surprisingly complicated formula reduced to, of course, there's a lot of reductions, reduced to a simple fact that there's one line passing through 2 points. Okay? So that was the argument that appeared here, 2000. Okay? And that is what I said earlier. Okay? And in fact, also, in a subsequent work with Jim Bryant, that we also compute a similar formula for abelian surfaces. And the reason of abelian surfaces, these are K-free and abelian surfaces are the only 2 Calabi-Yau manifold of dimension 2. Okay? And for abelian surface, there are new issues that come in because there are non-trivial linear systems. Okay? Family of linear systems. And then this whole Yau-Saz formula later was more generalized to a very general formula called Gaucher-Yau-Saz formula for all surfaces. That means that all surfaces can be computed with some behavior similar to this one. This is amazing conjecture. But however, in fact, eventually the proof of the Gaucher-Yau-Saz formula, we have to use this original Yau-Saz formula to do this computation. There was such a universality property, and that's not really computation. This is the only computation that we need to know. Okay, okay. And Yau-Saz formula for non-primitive class was later proved by Clem and Thomas and other people many years later. Okay, so here's another very different type of thing that I study when I look at mirror symmetry. Mirror symmetry is really, from physics, is a study of string theory in dimension 10 reduced on a Calabi-Yau free flow. And in physics, the more general physical theory is the M theory on G2 manifold. and F theory on spin-7 manifold. Okay? So then I'll try to understand, okay, what are all these manifolds? What is G2 manifold and spin-7 manifold? And also related to Calabi-Yau manifold. It turned out that they are, in the mathematics, many years ago in the 50s, in fact, a study by Berger, we classify all possible reduced holonomy group. What does holonomy group mean? Meaning that all possible geometric structure on the manifold, on the Riemannian manifold. Okay, so this is a classification of the type of structure. This is a full classification. There are only two types. The first type is things that most of the things that you see, like a Riemannian manifold, Kähler manifold, Calabi-Yau manifold, quaternion, and hyperkähler manifold. And beside all these, which work in any dimensions, there are only two extra. One is a very special one, G2 and spin-7 manifold. For many years, there are many mathematicians are interested in it because they're too special. But it turned out they are, from physical perspective, they are the most natural one, and they give you everything, basically. There's a unified field theory come from here. Okay, and then the other type is even more special one, and they are our symmetric spaces. Okay, now, so there's lots of these different type, and especially G2 and spin-7. So the question I ask is there a way to understand all this in a more mathematical unified way to understand all this structure? So they come from two different worlds. One is on the type 1, and the other is on symmetric space. Okay, so for the G2 and spin-7 is the following. This is so this is G2 and spin-7 here, and then these are all the other in the Berger classifications. And the perspective that I describe is all this can be described into geometry over real, complex, quaternion, and octonions, which are all the algebra with a norm. So these are classification of norm algebra, and then use that to classify all the norm metric geometry. Okay? And so there are 4 different norm algebra, and then of each of them, you can look at geometry which are non-orientable or orientable. Orientability in terms of the corresponding algebra structure. Okay? So this gives exactly all of this. And the reason that we don't look at G2 and spin-7 as much as before, because these are defined over the octonion, rather, which is a non-associative algebra. Yeah. Okay? And this description, in fact, more than just giving a description, a unified way of explaining different type of holonomy group, in fact, they understand all the geometry of all the geometric structure underlying the corresponding geometry. They include, well, the Lagrangian submanifold and the various bundle. And these are exactly the type of object we study in mirror symmetry. For example, in mirror symmetry, we look at the mirror correspond to Lagrangian or holomorphic bundle. Special Lagrangians are Hermitian-Yamu bundle. But the thing is, this type of structure go into every geometry here, including like a complex Lagrangian, associated submanifold, Kähler submanifold, DT bundle, and so on. Okay? So this gives a very nice unified way of explaining classification of all the geometry and geometric structure in terms of algebraic structure in a unified way. So these are all those most of the space, except those which are symmetric space. Okay, and symmetric space are classified by Eric Catan many years ago in terms of Lie theory, and these are all of them. You see, this is too many. And now the theorem that I prove is, in fact, you can interpret all of them as Grassmannians. While some of them are obviously like a real Grassmannian, complex Grassmannian, quaternion Grassmannians, and this Lagrangian Grassmannian, and so on. Okay? And in fact, you can explain all of them as Grassmannians. And what are they? Well, they can be complex Lagrangians, Lagrangian Grassmannian, or maximized isotropic subspaces. Not just in terms of one norm division algebra. So now both A and B are one of these norm division algebra. It can be both 2 of them. That's why you don't see those earlier, so some of the E6, E7 here. So all of this, you have like 27 different types of this. In fact, they're all Grassmannian of some particular type. Okay? So now the upshot of this is you can understand all the metric geometry in terms of all the norm algebra. Everything will become very simple, heuristically very simple. Okay? And this also leads to many new predictions and new duality and so on, so which I suppress here. And another way of understanding this, I introduced so-called vector cross-product geometry, which I don't have time to do it today. All right. All right, so let's go to the SYZ and mirror symmetry conjecture. So again, here we have two Calabi-Yau manifolds which are mirror. So the first type is this Candelas group, which understanding the symplectic structure on one side is really the complex geometry on the other side. In the symplectic structure, even though it might look simple, but in fact they are very complicated because of the quantum correction related to the quantum cohomology of the space. And then the identification between them is also highly non-trivial map. It's called the mirror map. And this understanding is leading to the enumerative question of, for example, counting rational curve on quintic freeform. Okay? And then there's a famous conservative homological mirror symmetry conjecture. It says that the category of Lagrangian and flat bundle on a symplectic manifold is equivalent to the category of coherent shift on the other side. So this has been a conjecture which has driven lots of study in mirror symmetry. And most of the study is really rely on doing computation on each side and then check that it's correct. Except that now this SYZ proposal by Strominger, Yau, and Zaslow really give you a geometric way of understanding what is happening in mirror symmetry, why that has to be these two seemingly completely different physics and geometry look the same, exactly the same. Okay. The first important part is how do you go from Y to Y track? That is a very mysterious thing. And then SYZ proposal said that if a Y track is a moduli space of special Lagrangian, torus on Y. Okay. So this is telling you how they are related. Okay. And that's usually referred to so-called dual special Lagrangian fibrations. Okay. So once you understand Y track is really a geometric way coming from Y, then you can try to understand how to interchange the two geometry going from one to the other side, because the other side is a moduli space. And that is called the Fourier-Mukai transform. Okay. Okay. So so a lot of my early work was focused on things to understand how to understand the SYZ mirror symmetry. Okay. So this proposal is saying Y track is the moduli space, but it's extremely complicated to do that because of the quantum correction. Okay. So first we have some work that this is a work which is not involving the correction part, and then you can want to see exactly what should happen module the correction. So this is a work I did with Yau and Zaslow. Okay, so if you are in the semi-flat case, this is really corresponding to the last structure limit of the Calabi-Yau. In that case, all the quantum correction is being suppressed. So okay, there's no quantum correction in this setting. Can you understand the interchange of these two types of geometry? And that was we are doing lots of this construction about this Fourier type and Legendre type transformation. They give you exactly how you interchange the two types of geometry. And for example, the deformed Hermitian-Yang-Mills equations on one side is exactly transformed by the special Lagrangian on the other side, and so on. And then another work with Kumarava, also at the same time, then we understand, we describe toric mirror symmetry via brane configuration in the 10-dimensional space-time. This is a more physical argument here, and that has been leading to some even very recent study on the brane theory in 10 dimensions. Okay, so this is when there's no correction. Now the difficulty is when there's correction, how do you do that? Okay, so this is a work I did with Kowai Chen and Xiuchang Lao. Okay, it's how do you realize the SYZ construction? Given a Calabi-Yau, how do you construct a mirror? Okay, so in general, it's too difficult. Okay, so that's the first type is the one thing which can have a more explicit description of Calabi-Yau structure, which are Calabi-Yau which has a toric structure, meaning that you have a large symmetry group of abelian symmetry. So there's the Calabi-Yau with large abelian symmetry are called toric. So in this case, we really realized this SYZ constructions, and then this is so-called T-derivative also called SYZ constructions. But the thing is, you have to do this quantum correction thing. Okay, and in fact, once we did that, there's a unexpected discovery that this mirror map that I introduced and mentioned earlier turned out to be not just an arbitrary map; they are really enumerative, meaning counting some particular one. Okay, so that was unexpected. Okay, so this is just a, if you like, this is an explicit example of what is a Y and Y check here. Okay. And this is the first realization of this whole SYZ constructions for the Calabi-Yau, and when it is a toric, okay, when it has a abelian symmetry. And how to prove that? Well, as again, how to construct a mirror is because it's toric, you have a lot of symmetry, you have a Lagrangian vibration, so on, and then you can look at the dual vibration. And then the dual vibration is locally given by Mori-Cartan charts. So you have different charts, and then you have to glue those charts together. And you have to glue those charts and the so-called wall-crossing argument, wall-crossing formula. And the most difficult thing, most essential thing, is to compute the quantum correction to give you the gluing data. So those are, we're going to put a star here. So the so-called quantum correction is really computing open Gromov-Witten invariants, and which is a notoriously difficult thing to compute. Unlike Gromov-Witten invariant, you can compute using algebraic geometry and localization argument. And this is something that you cannot, so we have to introduce a capping technique to do so. Okay. And then later, after several years, in fact, we generalized this to not just Calabi-Yau, to all the toric, and even toric is okay. And the most important difficulty here is that we are not assuming that the first Chern class is 0 or the first Chern class is positive. There's no such assumption at all. Any toric, and then you can construct, in this case, the Nagelsmann model. And then this is because we several years to really fully develop this capping technique to handle all cases without final Calabi-Yau assumption. And the thing is that we relate open Gromov-Witten to closed Gromov-Witten invariant, and then you can compute that later. And then you have to combine with various degeneration techniques. And that was the way to prove this theorem. Okay, so now still the main thing is how to construct the SYZ mirror in general, not having an abelian symmetry, not toric at all. Okay, so this is they try to do this in general. So the idea was the following: if you try to show that Y and Y check a mirror, we try to construct the SYZ mirror. Okay, they are just too nonlinear. You can't do it at all. So you first degenerate to a semi-flat case, which is things which are relatively more linear, means more like toric case. You first degenerate to this large volume limit, and on there you can try to do this dual transformations, but this is singular though. And then to get the so-called large complex structure limit. And then you have to deform from this singular infinity back to some finite case, and then try to do that. And that's the SYZ proposal, that how to realize that. Okay. So if you try to go to the large limit, okay, things become infinity. So therefore, eventually this limit, so-called semi-flat limit, this is what I call here, should be having a Lagrangian vibration over a base, but things are singular because the reason is this: Lagrangian vibrations can have singularity. The singularity will correspond to having holomorphic disk along some particular directions. So those directions will form a wall in this R5 space, R5 manifold, singular R5 manifold B here. So these are those walls arising from holomorphic curve, okay, on the space. And then when the wall collide, they're supposed to produce new wall. Those are extremely complicated procedure, and those are called the scattering diagram introduced by Kontsevich, Zauberman, and then studied by Gross and Siebert, and so on. And then those scattering diagram data can be used to control smoothing from this side. Okay, so that was the scheme, basically. Okay, so this is a sequence of work. We did it for many years to finish this. Is this wall, remember, what is the wall? The wall corresponds to, you try to understand the singularity of the Lagrangian fiber, and then they will give you holomorphic disk, and then they give you the wall here in the base. Okay, now we want to understand the wall more geometrically. So the wall, so this is supposed to be a wall. You want to think about the wall, we shall smooth the wall as like a delta function thing. Okay, so the wall will become kind of a delta function. So it will become a 0-1 form, close to a delta function shape 0-1 form, with value in the tangent bundle. That is important because the tangent bundle is, this thing is governing the deformation of complex structure. Okay, now the thing is, if you have two walls come together like this, W1 and W2, the two walls come together, they're supposed to expect to see new walls coming out to propagate the holomorphic disk. How does this happen? What is this happening? How is that related to the formation of complex structure? And the thing is, this is the formation of complex structure. So if two add together, they don't commute. So in fact, they don't solve holomorphic structure equation. This is a Mori-Cartan equation that governs the deformation of complex structure. The thing is, if you just add them together, they are not really the solution near W1, W2. The honest solution has to add more terms. Those terms are all like delta functions. Okay? So this is a very differential geometric and differential form perspective to see how the scattering arise. The scattering wall is really arise as a limit of some delta function solution for the Morikatani equations. Okay? The upshot is say that solving this deformation of complex structure is really the one that produced the that can be used to construct the large complex structure limit on the other side. And that in the two-dimension case, this is the analog what people study called the cosmic string in 2 dimensions, but it's much more complicated in higher dimension here. If we solve that, well, this is like a Witten-Morse theory type argument by looking at gradient flow using this delta function type harmonic form. And in the Witten-Morse theory, people study the round theory and look at a closed form and so on. But you have to deform the D operator by looking at F divided by H bar. But this is not that type because now we are deforming complex structure. The equation is non-linear, and also the differential form has a value in the tangent bundle. Okay? So this is we have to invent this theory to do so. Okay. Okay. So we'll explain that a little bit more of that later. Then once you do that, that really explains that how to get this limiting behavior away from the singular set, because this is scattering. This happens when this wall collide. How about at the singular set where the singular fiber appear? How do you do that? Okay. So this is you have to really solve the equation globally by near all those singular fibers. You have to glue those singular models. This is a completely different argument now. Okay. So this is something we did later. Then we have to control this DGLA structure. So originally, you only look at one form. Now you have to look at all the differential forms. These are called polyvector field, or the vector field, polyvector field. So this is what they call PV. This is more than one vector field. But I have to construct this algebraically because there's, you have to do this local model. And this has more than just differential form, differential gradient algebra. There are lots more structure here that you have to encode, and which make the gluing argument extremely involved. Okay? And then once you glue those things, then you can start to solve those equations from infinity by those Bogopolov 10th order of argument. That is not as complicated. This is gluing argument is very complicated. And then once you do that, then you find a solution phi by solving this equation. We have to look at the behavior of the solution to really get the scattering picture globally, not just near the intersection. They're everywhere. This is then we have to really, so this is appear in form of pi just earlier this year. And then this really gives you constructing this mirror space, SYZ construction, away from the singular set. So this is what I call this SYZ construction of the mirror after all these years, more than 10 years work. Okay? And more than just constructing the mirror, this has, because of all this construction we have a lot of structure that we understand. For example, this can be used to give you a DGBV structure and semi-infinite variation Hall structure on the moduli space and so on. Okay? So this come as a corollary of this construction. A few words about how to prove this theorem. Anyway, a lot of argument here, but the main difficult, non-trivial thing is we have to develop the whole Witten-Morse argument using this WKB type argument. It's asymptotic analysis when k go to infinity for this total deformation of complex structure. So we develop this and then try to use that to this calculation. Okay. Now we turn to a very different type of mathematics arising from mirror symmetry. Mirror symmetry predicts that if the original variable y has two large volume limit, then you may have two different mirrors that could be very different. Then you're not birational. There's just two different mirrors. However, the physics may be the same. So the derived category of coherence should be the same. Example, we call the Farfian Grassmannian correspondence. And a way to powerful tools to do this calculation is this one introduced by Kuznetsov about homological projective duality. And by studying this, we generalize this Kuznetsov result. This is a work early this decade. This is called categorical Pucher formula, meaning the following. If you have y and y pi, they are homological projective dual. You should think about this is a categorical version of a dual, classical dual projective dual variety. Okay, from y and then to y pi still, y2 and y2 pi still. Then the intersections, categorically, there are some isomorphism on the primitive part. Okay, to write down all this definition is extremely complicated, involve some orthogonal decomposition, Lefschetz decomposition, and lots of things to do that. But roughly speaking, this is a categorical intersection theory between y1 and y2 and the corresponding deal on the other side. So this is the formula. This is the categorical equivalence between the intersection of between deal variety. And why is called categorical Puka formula? In fact, if you have a categorical, instead of category, if you decategorize, become vector space, and decategorize again becomes some number. And this is the formula. This is the Puka formula I introduced many years ago. Why is this called a Puka formula? Because if you're looking at just on P2, curve on P2, this is really the classical Puka formula for curve and dual curve in CP2. So this is a huge generalization of the usual Puka formula in classical algebraic geometry, which are motivated from this huge amount of physics and math. Okay, and how to prove this formula? Okay, so we have to refine all this work of Kuznetsov and really because handling all this category, how it change under mutation is extremely complicated. The analogy, if you in subcategory, if you look at just vector space, it's much simpler, and this is like spectral sequence. So we have to introduce this notion. It's like a categorical analog of a spectral sequence, which makes it so much otherwise, it's, the calculation is too hugely involved. We can't do anything. Okay. So, and then this is how this transport game argument, that this whole method that we introduced, and then use that to prove this. And then this whole method become very powerful, and then give nowadays a lot of new application in understand the derived category of coherent shift. Okay. All right. So recently, there are new discovery in physics, so-called the 3D mirror symmetry, and it's really jointly discovered by mathematicians and physicists. Okay, so on the right-hand side, we discussed the Calabi-Yau geometry. This is a mirror symmetry between two Calabi-Yau, and the duality is between symplectic geometry and complex geometry. So the capital omega is holomorphic volume form, which governs the complex geometry. It's a duality between these two. On the object level, it interchange the two types of object. One is Lagrangians with flat bundle. The other are coherent shift. You can roughly think about the complex submanifold with holomorphic bundle of vector spaces. Okay, so the 3D mirror symmetry nowadays, I'm suppressing the physics part at the moment. The 3D is really to come from 3D n equal to 4 gauge theory. So mathematically, it's a duality between two hypercadal manifold rather than Calabi-Yau. The hypercadal manifold, you first fix the holomorphic symplectic form, which are called omega c. The 3D mirror symmetry will interchange the cadal structure with another structure, which is the so-called equivalence structure, which are just Hamiltonian C-star action. So in 3D, then the interchange will be cadal structure and equivalence structure. And on the object level, it's similar. Instead of Lagrangian and complex Lagrangian, now the object are both are complex Lagrangian. So complex Lagrangian in X and X sharp. And then now this is either a flat family of vector space or holomorphic family of vector space, right, in the 2D mirror symmetry. Now become a flat family of category or holomorphic family of category. Okay, so this is an analogy, a much more categorical, one more categorical version than the usual mirror symmetry. Here's a simplest example. 3D mirror symmetry. These are two hypercadal manifold. It's cotangent bundle of P2, and this is resolution of A2 singularity. Well, notice that there are different dimensions. Okay. Let me just show you a simple picture here. So this is a C1 with P1 here. So this is a kind of a hypertoric picture of cotangent bundle of P2, and this is the other one. Why I join? So the rho is the action. So there's a C-star action. I'm kind of thinking how the action direction. The free fixed points. So first notice that both are free fixed points. And then these are C1, C2, C3 are really the Lagrangian that people are will be concentrating on. Because the two spaces are really different dimensions, it's difficult to imagine that all the geometry are equivalent. Only this particular geometry, which are coming from the fixed point set, they are related to mirror to each other. So in this case, those are unstable submanifold or the attracting set. Is really these three particular Lagrangians, C1, C2, C3. They will be related to the other side will be C1 track, C2 track, and C3 track. Okay, these are related. Okay, and a lot of prediction in 3D mirror symmetry and related to geometric representation theory and so on. Okay, and so here is a proposal with my student Chen. Again, this is a really SYZ type proposal. It's giving a geometric explanation of why this very mysterious duality, how this has come about. Okay, so again, the same as before, we have to construct the 3D mirror, and then we have to transform it. The construction previously is moduli space of something. Now, you start from this hypercalar one. How to try to construct this? Okay. For each of these Lagrangian C1, C2, C3, we will look at is stringy moduli space of that. Okay. And then look at this cotangent bundle. And then you have to try to glue it together in a very subtle way. This is using the Lagrangian correspondence to glue that together. And that will work in this case, for example. Okay, so this gives you a geometric way to construct the mirror space from this one. Again, I mean, the whole process will be extremely complicated. Lots of technical issues that are involved. Okay, so that's why I call it proposal. And once you have this proposal, then because the mirror is related to the stringy moduli space of the submanifold inside C, so then how to relate all the two categories between all this geometry between the A side and B side here? That will be using the family Fukaya theory, okay? Because they're related to Fukaya category. Okay, so that is the thing. Okay, so in the remaining few minutes, let me explain. Is this different? It looks like a very different subject, but eventually, in the next slide, I'll show you that it's really related to our 3D mirror symmetry picture. So this is a series of work I did it with Chen and Li for many years. In fact, we have more than 15 papers on that. It's about how to understand quantization of Caylor manifold. Okay, so let me just because we have very little time, just give you a rough perspective of what we are doing here. There's a lot of things that I can say here. So we want to give a systematic way of understanding various different quantization scheme, for example, in the Caylor manifold case. So the deformation quantizations to deform the function to score quantum local observable to become a quantized. So this is deformation quantization. And geometric quantization is the Hilbert space is associated to. And then the action, how this one acts on that is called the Brazil-Thomas quantizations. And then from this local observable, you can go to global observable called the BV quantization, solve the quantum master equations, and then you do the algebraic trace, and then you will prove the one loop extent, and so on. And we have to understand when you can do this quantization, which is a non-formal way, meaning you can set h bar to be a fixed number. This notion of quantizable function with a differential operator, and a huge number of things. There are lots of different quantization schemes, but we developed a systematic way, just one unified theory to tackle all of them. This is a theory originated by Fedosov on the symplectic manifold for geometric deformation quantization. But we found that in the Caylor manifold, there's a very canonical way using generalizing the L infinity structure by Kaplanov to really to get a much more canonical structure to quantize the Caylor manifold using Fedosov type approach, and then we further develop that to understand all this from this perspective. Okay. And why is that related to 3D mirror symmetry? For example, it's related to in the 3D. There's called a twisted trace, which is an ongoing project. Some of the ideas come from the following: if you start with a Caylor manifold, then the cotangent bundle has a locally as a hypercalar structure. Okay, that's just a holomorphic symplectic structure. So the M is now becoming a complex Lagrangian in this holomorphic symplectic space. And then the deformation quantization of M, deforming smooth function on M, it really is essentially the same as a holomorphic deformation quantization for a holomorphic function on X. In fact, to do so, you have to do a twisted rotated complex structure. So therefore, this structure that we look at, quantization of Caylor manifold, become part of the data in the brane quantization of the space X, okay, and so on. And this related to the study in representation theory called the category O, another part of the geometric representation. And then our aim is to further to use this Caylor quantization to give a geometric way to describe all of this structure. Okay. All right, so let me, in the last 0 minutes, let me give a conclusions. And the aim is all these are motivated from the physics study of string theory and its generalizations. we introduce lots of different techniques to handle different type of problem. Some are in differential geometry, algebraic geometry, symplectic geometry, quantization, and so on. And also we propose different perspectives to understand new theory, and we'll maybe explain that next time. Thank you.